Okay, so we're going to start this fourth section of the course, and this is what I call non-equilibrium concepts or systems. Everything that we're going to be doing for the next week or so is going to be on non-equilibrium systems. So things that flow. And like in electrochemical cells and batteries, we have the flow of charge. Now, they started out in physics, they didn't really, at the time, know what was moving in terms of current. And so they said that current was the flow of positive charge. Well, we now know it's the electrons that are actually mobile. So it's kind of interesting. So when we charge up the power lines, we're if it's DC current, you're sort of pulling electrons off of that wire and stuffing them into the ground, and then that wire is connected to something else that's connected to ground, and so then the electrons flow up through the ground in through that device, and then back to where you're pulling on them. So it's kind of backwards to what we think, but physics has defined that current is positive charge flow. So we'll see this in the batteries today. But it's definitely not an equilibrium system. So we're going to be talking about the basics. We're going to start with oxidation and reduction and redox chemistry today. So this should be a review of, let's see, is it Chem 1 or Chem 2? I covered it a little bit in Chem 1. We did oxidation and reduction and some on redox balancing. But this should be some review, but if it's not, that's good. We'll learn it in detail today. And then we're going to talk about the non-equilibrium chemistry. We use these redox reactions to make batteries. We also have these redox reactions happening in corrosion, and we try to stop that to protect the materials. There's like one slide on electroplating. It's pretty straightforward. And then metal equilibria. So let's jump into this thing that's moving the electrons and pushing the charge around in these systems, and that is electrical potential. And obviously, there's a spontaneous push, we call it electromotive force, driving these reactions forward. And we know that delta G is the characteristic that we look at for spontaneous reaction energy changes. And so this is the connection of delta G to the electromotive force, that electrical potential. So just like we have, gravitational potential, you got a ball on a hill, okay, and we can measure its potential energy. We also had chemical potential. So delta G is called chemical potential. And it's the potential present in chemicals, and they react spontaneously and go downhill, just like a ball goes downhill. Well, now we have electrical potential. So we call that voltage. So voltage is a measure of how high the hill is, and the ball on that hill is the electrical potential that is wanting to push electrons through a circuit. And this is a great equation. So I've highlighted it in yellow. This is actually a great way to measure delta G of reaction. If you can figure out how to get a voltage out of the system and measure how hard that system's pushing on electrons, then that's related to delta G by Faraday's constant. That's what the F is, and the number of electrons in that reaction. So F is Faraday's constant. It's 96,485 coulombs per mole. So that's the charge on a mole. You could say like a mole of charges, and it's not a mole of electrons, because electrons have a really tiny, like 10 to the minus 19 coulombs. But anyway, you could get to what a mole of electrons is. But that's Faraday's constant. It's also related to Gibbs energy. It's joules per volt mole. So you can get convert basically from voltage to joules per mole of substance. Okay, and this is this reaction that that we have that calculates the delta G from some standard delta G values plus some correction factor. So think about this. This is a standard delta G for the reaction, but we're not at equilibrium. Okay, and so there's some other correction factor. Remember that Q in this case, well, now we've got our third Q actually. Let's talk about that. We've talked about Q being the partition function, and when we used capital Q, it was the partition function, the ensemble partition function. And then we had Q for heat, okay? And now we've got Q, and this is the Gen Chem 2 version of Q. This is the reaction quotient. So you see over here products over reactants, the concentration of the products over the concentration of the reactants. Okay, so we call that Q. And we're going to use Q because we're not at equilibrium. Okay, if we were at equilibrium, Q would equal K. And so the subscript or superscript 0 means the standard conditions, 25C and 1 molar solutions. And so that's what you have for the delta G 0. And then Q would be those situations when you're not at 25C or when you're not at 1 molar solution. So that'd be your actual system, your products over your reactants. And so then we can put in our NFEs, okay? And then we have something that we would see as the standard potential. If a standard gives energy, that would give us a standard potential, okay? And then we have this correction factor, which gives us our actual potential. And so we could solve for that actual potential, bring that NF over on the other side. It cancels from the standard potential, but then this RT over, this minus RT over NF, this constant out front is a function of the number of moles in the system and then also the temperature of the system. So this is where we get the Nernst equation. I'm thinking Gen Chem 2, you'll probably use the Nernst equation. And so at standard conditions with 298, we have this value here that's given in the textbooks for the Nernst equation. That's 0.02569, but that's for the natural log. If we want to convert that over to base 10 log, okay, then we have a factor of 2.303 that comes out front. And when you multiply that 2.3 times the 0.025, you get the 0.059. So this is the log base 10 version of the Nernst equation. And you have to know the number of electrons that are pushed through the circuit, and then that'll give you the actual voltage of that cell. Yes. I did that mainly just because this is the traditional version of the Nernst equation using the base 10 law. But you could use either one. You just got to make sure. So that's the other thing too, is a lot of times these you don't see what's in this constant. You just see volts. But this constant is RT over F. It's Faraday's constant. It's the gas constant. It's the temperature. So this number here, I actually don't like using this number because it's not, it's for a single temperature, 298. Whereas if you leave it up there as RT over F, then you can put in the different temperature. So far that E0, all the solutions have been 1 molar. And so we can actually see what happens when they're not 1 molar. So if we've got this equation, look carefully at the states of matter. Okay, so let me sit on that for a little bit. We've got solids and we've got aqueous solutions. Remember from Gen Chem that we're looking at concentrations, and so we don't use the solids, we don't use pure liquids. We only look at those things where concentrations change dramatically. So the aqueous things are the only thing that show up. And so if we're looking at this, we can push this reaction forward or backwards using concentrations that are not 1 molar. So that the standard cell, the standard cell was using 1 molar concentrations. The actual cell uses these here. So here we're looking at aluminum 3 plus is 2 molar. So we got 2 molar here and 1 molar here. So do you think that made the potential of this reaction higher or lower? Yeah, and we're using this part of our brain. So what are we doing with Le Chatelier? We're pushing the reaction or pulling it. Yeah. And so in this case, we've got products that are higher than 1 molar. And so that's going to be pushing it backwards or putting negative or reverse pressure on the reaction. And so that's going to reduce our cell potential. So our actual potential will be less than the standard because the standard is at 1 molar. And if the products are already too concentrated, it's going to push less hard. Okay, what if we swap that? We made manganese 2 molar and aluminum 1 molar, then it would push harder because we've got more reactants than the standard situation. So it's going to push forward a little harder. So we'd have a higher potential. And again, so that potential is the number of volts this reaction produces. And we can control that voltage by changing the concentrations. That's the take-home lesson. And the point is, galvanic cells are not at equilibrium, so we use Q and not K. So we're looking to see if that Q is, getting higher or getting lower, and it's where it's pushing more or less. Okay. And so this would be the equation for how we would calculate that. We would have this E cell of 48. It would go right here. Then we could put our concentrations in here, and notice it's a negative sign, right? So this log is greater than 1, and it gets more greater than 1. You're going to have a positive number, but then you're going to pull down the voltage because your products are too concentrated. And so you're going to correct that voltage down. The opposite, if you have lots of reactants and you're pushing that reactant higher, if all of your concentrations are 1 molar, then it's a log of 1, which is 0, so there's no correction. But if you make it less than 1, then you've got more reactants, and so that's going to push that reaction forward because a log of something less than 1 is negative. And so that's going to change the sign to a positive, and it's going to correct the voltage up and make it more, make that potential higher. The opposite if you've got more products. N? Good question. We're going to get to that. Yeah, that's a good question. Now, in this reaction, it's pretty easy. So we're looking at how many charges, how many electrons are moved. So this went from 0 to 2 times 3 plus. So 6 electrons have come off the aluminum and gone onto the manganese. Here's 3 times 2. So 6 electrons, so N would equal 6. So it's easy in some situations to know what N is. But today we're going to balance redox reactions where looking at it, just looking at the reaction unbalanced, it's really hard to tell. And so you got to actually balance it and then figure out what N is. So let's do a calculation with the Nernst potential, or Nernst calculation. So here we've got a really low concentration of our products and a larger concentration of our reactants. And so we should have an increase in our cell potential. So here's our reaction, our Nernst equation. And so we're going to have that 48 over here. And look at this. This is much less than 1. We got 0.001 squared, and so it's going to be 0.0001, and divided by 8 natural log. Okay, so this is the correction that we get. So all of this piece, this log it comes out to be negative, and so that changes this positive sign here, changes it to a positive, and then all of these values give us a 0.07 correction in voltage. So it made it, 0.07 volts higher. Doesn't sound like a lot when you consider, 0.001, so 100th or 1,000th of a molar, concentration of aluminum. But this isn't a very powerful cell either, 0.48. So as the galvanic cell reaches equilibrium, the cell decreases. At equilibrium, E cell is equal to 0. So this is why a battery goes dead. And so I've always thought this would be a fun money-making scheme for, if you were a corrupt person, you could sell really safe, pre-equilibrated batteries. And people were like, oh, okay. Because they're safe, they're at equilibrium, which means they're dead. So, a gullible buyer. So let's look at what's going on inside the battery. This voltaic cell is a way to think about the battery. They're all essentially like this, but they're not necessarily made of aqueous solutions with salt bridges and stuff like that. They still have some sort of interface, and they still have to have something to move the positive components and the negative components. So in spontaneous reactions, these electrons are transferred and energy is released. We call this a voltaic cell. So here's a picture of the voltaic cell. And so this is what I was saying about the positive charge moving this way. You see, look at the sodium ion. So the sodium ion's moving to the right in this situation. The electrons, so then the positive charge, if you were to be like a physicist and talk about positive charge is moving, it's really the electrons that are moving, but you could describe that as positive charge moving. So counterclockwise in this circle would be the positive charge, clockwise would be the negative charges. So here's the ions moving, here's the nitrate ion moving in a clockwise manner, the electrons are moving. So then there's a reaction that takes place at these electrodes. So notice here the electrode zinc goes from zinc 0, which is zinc solid 0 here, to zinc 2 plus. So again, that's that counterclockwise movement. Over here, the copper 2 plus is plating out on this copper 0 cathode. So it's going from copper 2 plus to copper 0. So this cathode here is getting heavier. This zinc anode is losing. So eventually that zinc cathode will be completely eaten away and the battery will die. If it doesn't reach equilibrium before then it will die when the electrode gets broken. That's what happens with your automobile batteries too. The lead, one of those lead electrodes is being chewed up, and then when you recharge your battery, it gets built up again. Well, it doesn't always structurally strengthen that plate when it's being recharged, and so eventually one of those plates breaks, and you have a broken cell inside your battery, and it's dead and not able to be charged. So this is the galvanic cell, and this is the spontaneous voltage that it generates, 1.1 volts. So a zinc copper cell will give you 1.1 volts with 1 molar solutions of zinc and copper ions in those beakers. Now you need to connect the circuit, so you need this salt bridge. And so this salt bridge here I'm just going to call the ion conductor. You can pump electrons through a wire way faster than you conduct ions through an ion conductor. And so this battery will be limited in its ability to produce amps, the amount of current flowing, by that salt conductor. And that's the real trick in batteries, is to get an ion conductor that can handle, lots and lots of amps. Because when you want to put a lot of current through these motors, you need a lot of current, you need a lot of charge to flow. And your ions are big, bulky things compared to electrons. An electron is 1,000th of the mass of a proton. 1,000th. Okay, so even if you were just pushing protons, you're pushing 1,000 times more mass than you're pushing electrons. So this is a way to remember what happens at each of the electrodes. You have reduction and oxidation. And so this is my memory trick. You've got your galvanic cell, okay? And oxidation takes place at the anode. Notice how your anodes and your cathodes go down into the solution. And so you can connect an anode and a cathode to the words oxidation and reduction. You can't put cathode on oxidation because there's no C in that word, okay? And you can't put anode on reduction because there's no A in that word. So this is my own memory trick. I've thought of this one day sitting in my office. I was like, that works. Plus the anodes and the cathodes go down into the beakers. And so this is a great way to think about it. So oxidation takes place at the anode. You can see that here. The zinc metal is 0 formal charge, and it's becoming a cation with an oxidation state of 2+. And over here, reduction is taking place at the cathode. Here you've got copper 2 plus becoming copper 0. So its oxidation state is being reduced from 2 to 0. So you have reduction. And you have that memory device, oil rig. Do y'all remember that? Oxidation is loss of electrons, and reduction is gain of electrons. So this copper 2 plus is gaining electrons to become copper 0, and this zinc 0 is losing electrons to become zinc 2 plus. Yeah, so there's for like lithium ion batteries, I think that the liquid that's in there is propylene carbonate. It stabilizes the lithium ion, but it's not an aqueous solution. But you still need something to move those ions, and so that's the trick. And so there's a lot of technology that goes into those in producing an ability for the ions to move. Now we have all of these reactions written out in standard reduction potential tables. You can see these in the back of the book. And now first thing you want to do is look to see if it's an alphabetical list or if it's listed by reduction potential. Okay, if it's an alphabetical list, then what I have on this screen is totally bogus. Okay, but if it's listed by potential, if you notice, if it's sorted from high to low, and so you hear what I'm saying? I'm saying if, right? This is an if-then statement. If it's sorted from high to low, then clockwise pairings of these reactions are spontaneous. Okay. So what do I mean by that? Well, we've got the forward reaction. These are all reductions, and so the forward reaction is a reduction, and if you run a reaction of one of these backwards, it's an oxidation. And so you have the reduction reaction minus the oxidation reaction. When you say minus, essentially you're saying take that reaction and flip it, okay, and add that. So here we have the hydrogen, the acid proton receiving 2 electrons to make hydrogen gas. That one by definition is 0 volts. Remember when we came up with our entropy table, we said we needed a reference. Where's 0 in the table? We said absolute 0 Kelvin was 0 for entropy. And so we could make standard entropies. And then we had enthalpies. We said elements in their standard states were 0. So sometimes we just make an arbitrary choice. We say elements in their standard states have 0 enthalpy of formation or 0 Gibbs energy of formation. And so then we can make a table relative to the elements. In the reduction potential table, we've defined voltage based on the hydrogen, acid protons making hydrogen. So they make a little hydrogen cell where they're bubbling hydrogen gas in there, and they've got an acid, 1 molar acid, and they measure like a zinc electrode or copper electrode relative to that standard hydrogen cell, and then they can get the voltage for the reduction reaction for copper or the reduction reaction for zinc or whatever. And so we've defined the hydrogen potential as 0, and everything relative to that is in the table. So what we have then is this forward reaction, the reduction is 0. Then we subtract the oxidation. And so here we have the lithium reduction is -305. By subtracting that, we're saying run that reaction backwards and call that the oxidation. And so then we end up with a positive 3.05 volts. So that would be a really nice battery, but it's not very functional, right? Because we got to have hydrogen gas. Acid's easy. We got lots of acids, but we're not going to run around with hydrogen gas, okay? But it would give 3 volts. That wouldn't be a bad cell to have instead of your AA batteries are 1.5 volts. A 3 volt battery, sometimes you pair those 1.5 volt batteries together. You get 2 batteries in there in series, and you get a 3 volt system. You could use 2 of those AA's, or if you had this battery, you could just use 1, and that cell would produce 3 volts. You could move up the ways a little bit, and you could have, let's find one that's easy. Up there, the bromine cell at 1 volt. So if we ran the bromine, liquid bromine to make bromide, in the forward direction, that's a reduction, and paired that with lithium, then we would have 4 volts. We could have a 4-volt cell. So you see what I'm doing? Clockwise pairings. And so that means that these are the reactants. Let me circle them. So lithium and bromine liquid would be the reactants because we're running this one backwards. So this arrow would go the other way. Okay, and that would change this value to a positive value, and then we'd add the voltages. And then the products would be the bromide and the lithium ion. And so that would give us a 4-volt potential. In this particular case, the highest one would be fluorine. I don't really run around with fluorine gas, but if we did, that would be a really good one. That's 2.87, and this is 3. So if we swap the sign on this, that would give us a 5.87 volt battery. So that would be nice. We could almost replace, 4 AA's with that. This would be 6 volts, 4 AA's, and here we've got almost 6 volts just with a single cell. So this is how they come up with the different cells for the batteries, and they fine tune them with concentration. Okay. So that's one way to use this potential standard reaction potentials table. So we talk about oxidation numbers, and so this is one feature though that we need to make sure we understand is if you've got a species bonded to itself, whether it be like the bromine example, Br2, liquid, okay, any element bonded with itself is going to have a 0 oxidation number. So it'll be 0 or 0. We tend to show the charge on the elements when we are showing ions. And so if this gives a Br minus, then it would be a -1 oxidation number for that element. +2 for zinc +2 plus, etc. So we can keep track of those oxidation numbers. And that is one way to know what was reduced and what was oxidized. I like the word reduced because this number was reduced, right? And so the H plus had an oxidation number of +1. It went to 0. It was reduced. Okay. How did it do that? Well, it gained electrons. So reduction is gain of electrons. That's the other way to think of it. And then oxidation number for zinc went from 0 to +2. It went up. It was oxidized. Okay. Now, what about the 0 to -1? So bromine liquid goes to -1. It was still reduced, right? It went from 0 to -1. Even though it now has a non-zero oxidation number, it's -1 is lower than 0, so it was reduced, and it gained electrons to do that. Okay, so now let's get into the main point of today's lecture, because this is the thing that I'm going to be testing you on, and it's balancing redox reactions. Now, this is way better than Sudoku. I like doing these, and I always did. I remember getting wrapped around the axle when I was in Gen Chem. Okay, this is one of my memories from back when I was a child in Gen Chem. And I didn't follow these steps in order. And so now you change one thing, and then it changes this thing, and then you change that, and then it requires something to change over here. And I just kept adding waters and this and that. And I remember going with my pencil for a whole page of changes. And I thought, when is this ever going to end? Okay. And you'll see why. If you follow these steps in order, though, you're guaranteed to end. All right. So here's the half reaction method. You break the reaction into 2 half reactions, and maybe 95% of the time, maybe 99, it'll be obvious what the half reactions are. Sometimes, like rare cases, it's not. Okay. Then you balance each half reaction. And then here's how you do that. So you balance the elements other than hydrogen and oxygen. So you leave those elements alone at first. Then you balance the oxygens, but you don't put oxygen gas on one side or the other. You use waters to balance the oxygens. Okay. Because most of these, well, all of the ones we're going to deal with are in aqueous solution. So there's water around, and we're swapping partners. We're changing bonds and moving electrons around. So we will destroy water molecules. So it'll grab oxygen from water and produce acid protons and so on. Or acid protons will react and produce water, depending on which side they're on. And then we balance those hydrogens that we've added. So, sometimes your reaction won't have any hydrogen to start with, and then all of a sudden you start putting waters in there. And now all of a sudden you're adding hydrogen to the reaction. So we don't want to balance it with hydrogen gas, we want to balance it with aqueous protons. And then lastly, we balance the charge by adding electrons. And then we multiply those half reactions by integers so that the electrons gained and lost are the same. So we'll have one half reaction that produces electrons and one half reaction that consumes them. And they have to handshake. So if one produces 5 electrons and the other one only consumes 3, then we got to find some integer multiple of 5 and 3 that where they have the same value. So we'd multiply the 5 by 3 and the 3 by 5, and we have 15 electrons produced and 15 electrons consumed. And then we add those half reactions together to make our whole final balanced equation. And then we're going to probably have waters on both sides and acid protons on both sides. And so if we have 8 waters on the right and 3 waters on the left, we're going to subtract 3 from both sides. And we'll just have a net of 5 on one side. So let's do this simple reaction. This is a titration reaction that we have using permanganate. This is a redox titration to find out how much oxalate is in solution. Okay, so here's our system. We're using permanganate to titrate the oxalate, and our final product will be CO2, which comes out from the oxalate, and then the manganese 2+ cation. I love this I love permanganate as a redox titration. I like it as a reagent because when you do a titration, you need a color change. Okay, well, permanganate is its own color change, right? So you put a little permanganate in that solution. If there's oxalate in there, it gets destroyed. This is purple. This is not. And so as long as you have some of this in the flask, your purple color goes away. As soon as you run out of this, you put another drop of permanganate in there and you get a colored solution. Now, if you go this dark, you've blown way past the endpoint. So don't follow their advice there. That's way past the endpoint. But a little drop where it turns pink and you swirl it and it doesn't go away, it doesn't fade, then you know you've gotten past you're at the endpoint. Okay, so let's look at the half reaction. See what I mean by being obvious? The half reactions, you've got a manganese here and here, so that's one half reaction. That the carbon here and here, that's the other half reaction. So we're going to balance those separately. So let's balance the carbon first. So we have the carbon half reaction. First step was balance the elements other than hydrogen and oxygen. Okay, so we add a coefficient of 2 on the CO2. Okay, you see that. Now we balance the oxygens by adding waters. So see, we don't have any hydrogens in this reaction at all. But it turns out the oxygens are balanced. So we got 4 on either side, so we don't have to add waters. We can balance the charge by adding 2 electrons to the right side. Now, notice that in this case, we're not able to get the charges on both sides to equal 0. That's not the goal. It's not to make the charges 0, it's to balance the charges. That's totally different than making it 0. So what we're doing is we're putting 2 electrons on the right side so that we have a -2 over here and a -2 over here. So now the charges are balanced. And then we can check to make sure they are. Yeah, they are balanced. So, and then we have our elements balanced and our charges are balanced. So we're done with this half reaction. Let's do the manganese half reaction. It's a little more involved. So we balance the elements other than oxygen and hydrogen, and sure enough, the manganese are balanced. So then we've got 4 oxygens on the left, so we need to add 4 waters on the right. So this complicates things because now we add some hydrogen, so we got to balance those. So we need 8 acid protons on the left. So we put 8, and that changes the charge. And so that's why we hold off on the electrons till the end, because as we start adding acid protons, we're going to screw up what we had with the electrons. We're going to have to add more electrons. And so we add those 8 positively charged protons on the left, and it looks like everything is balanced in terms of the elements. So then we balance the charge. And so here we have 8 positives. We have a +8 here, -1, and we need that to equal +2. Okay. And so a lot of people will mess this up. They'll see a +8 -1, so they have a +7 on the left, and they think they need to add 7 electrons. But that would be taking it to 0. We're not trying to get to 0. We're trying to get to +2 to make it balanced. And so we only need 5 electrons on the left to make it a +2. And so our -5 +8 -1 is equal to +2. So our charge is balanced. We can check the elements too. We have 8 hydrogens, 1 manganese, 4 oxygens on the left, and the same on the right. So if the charge is balanced and the elements balanced, you have a balanced half reaction. So we can check our work. I like this also because, again, like Sudoku, you can check your work. Is everybody caught up with me? You got it? All right, let's go to the next page where we bring these together. We evaluate the 2 half reactions together, and this is when we need to get them to handshake. So we're producing 2 electrons from the top reaction, and we need 5 for the bottom. So we're going to multiply the top reaction by 5 and the bottom reaction by 2. Since we can't get 2 to go into 5, we're going to have to come up with a common multiple, and so that would be 10. And so when we multiply the top reaction by 5, this is a place where people mess up. Typically, they'll get the electrons right, and they'll get the first one right. They'll see 5 times the oxalate, so they'll get that right. But this is the one they screw up. Okay, they'll bring a 2 CO2 down instead of a 10. Okay, so you got to make sure you multiply every species by that 5. And then the bottom one, we get 10 electrons, 16 protons, 2 permanganates, 2 manganese, and 8 waters. And so this is, when we add these together, this is our net reaction. And notice how the electrons are gone. So we acknowledge that those electrons from the top reaction have been donated to the bottom reaction and been consumed. Now, Hunter, when you asked about the N, that 10 electrons is the N in the Nernst equation. So for this reaction, we would have 10. And notice how you don't see that anywhere in this bottom one here. Right? So just looking at that reaction, it would be really hard to figure out that 10 electrons changed places. You could probably get it from the oxalate. I see a 5 times 2 minus. Yeah, but that would be the only place you see it. But you have lots of options, right? You got 16 plus here, so is in 16. You know, you got 2 is in 2. Is it 10? Is it 4? So you got 4 options for N just by looking at the species, and so you don't know which it is. So it's better to, to do some exploration. Now you can figure it out by digging into probably the oxidation numbers on this manganese. Um, and if you took the 4 oxygens and said those were -2, then each, and then you had the number of positives on the carbons, that's all. But again, it's better to get it from the half reactions. Also, we check the charges. We got a +16, -2, -10 for the oxalate equals a +4. And then all the elements check out too. So when we evaluate those half reactions together, we can look up the potential. So we need to get this from the table. So we could find that oxalate reaction. It would be written in reverse because this is the oxidation reaction. How do I know this is the oxidation? It's producing electrons. These are products. Oxidation reactions, the electrons are the products. Oxidation is loss. When you go past the arrow, you lost electrons. Does that make sense? They're products. And then reduction is gain. So when you go past the arrow, you have to have electrons to pass the arrow. And so sure enough, here's the electrons. So when you go past that arrow, they get consumed into the system. So they're gaining electrons. And so this reaction will be listed in the table, and you've got the reduction potential here. This is the reduction potential that you would find for oxalate. This reaction would be written backwards, and it would be a minus 0.49. And you reverse that sign to make it an oxidation because the reaction was reversed. And so you reverse the sign, and then you add them together. When you add them together, you get 2.0 volts. So that's the electrical potential of the system. Notice what we did not do. Can you see something fishy about this that most people make mistakes doing? Yeah, so we have that top reaction multiplied by 5, but we do not multiply the potential. Okay, so do not multiply the half potentials when you multiply the reactions. And the tables contain all of the reactions written as reductions, and so the oxidation reaction will always be backwards in the table. Now, the reason we don't multiply the half reaction potentials would be think about your gravitational potential when you're on the second floor. Okay, your gravitational potential on the second floor is the same whether there's one of you up there or 5 of you up there. Okay, because you're just still one floor up, and so the fact that there's 5 of you up there just means there could be a higher current going down the stairs, but it's not going to push any harder. Okay, and so multiplying these potentials just is like putting batteries in parallel. It's like we have 5 batteries instead of 1 battery, but there's still one volt, 1.5 volts or whatever. So multiplying, making the system bigger doesn't make a higher potential. Think of a waterfall. The height of the waterfall is the potential. The multiplying the reaction is just making the waterfall wider. More water can go over, but it's still got the same drop. So potential is the drop, not how wide the waterfall is.
Adding more would just extend the life.
Yes, the battery would have longer amp hours. Yeah, it could produce more amps for a longer period of time. Yeah, but not a higher voltage. Yeah. And so those potentials are the voltage that's put out. Now we have this shorthand called, this called line notation. We've only got 3 minutes, so I'm going to fly through this. But the point is that this is the main point right here, this general form. The oxidation reaction and the anode are written first, and then the reduction and cathode are written second. And how do you remember that? Well, think about alphabetic order. Anodes first, cathodes last. So A to C, that's alphabetical order. Oxidation is an O, reduction is an R. And so the electrodes are in alphabetical order, the reactions are in alphabetical order. And oxidation and anode always go together, and reduction and cathode always go together. So it's in alphabetical order that way. Now this vertical 2 bars here is there's a vertical line representing every junction. So every solid liquid boundary is a junction in these cells. So I've got some examples of line notation. I mean, we are out of time, but you can watch the video and get more commentary on this. as we go, but it's pretty much the same thing. The nice thing about having the tables, I'll give you reactions that are not in the table to test your ability to balance redox reactions. But in most cases, I just go to the table and find they're already balanced in the tables. So that permanganate reaction is in the table already balanced. And so is the oxalate reaction and all of those. So you can just go to the table, reverse one of them, pair them together, and you've got your reaction. And it tells you how many electrons they produce, so you know how many to multiply by, and you can get in that way. Okay. This is how we figure out what voltages we want. So again, you've got the reduction and the oxidation. You're going to flip the oxidation. And so here's all of the different options for these 5 elements: gold, silver, copper, iron, zinc. Okay. And if you just take the upper minus the lower, plus 8 minus this negative 76, you get a 1.56 battery. So a silver zinc battery would be 1.56. So you can do this with all the different elements, and that's how you would select which elements you want to use to make your batteries. Now there's reasons like cost. You may not want to use silver because silver is expensive. So you want to find, elements that are cheap but also give you the right voltage, and also typically small ions because they're able to be conducted quickly. So that's what helps our lithium ion batteries. Is lithium is a small cation, and it can move through the barriers in these batteries and give you a high current. Now we talked about series and parallel. So if we put batteries in series, the voltages add. It's like stacking them one on top of each other, and so there you have a waterfall on top of a waterfall. And so you're changing the height of the waterfall, but if it's the same type of battery, you still have limited current. If you put them in parallel, you can increase the current. And then we just have a survey of batteries. Some of these use oxygen in the air, so they have a little gasket in here, so air is one of the reactants. So that's kind of nice. Here's our automobile battery. This one's kind of cool because we've got a lead electrode here and a lead oxide electrode, and they both consume sulfuric acid. And so sulfuric acid is being consumed in the battery reaction. And then when you charge it back up, you're producing sulfuric acid. My family's had bad luck with batteries. We've had 3 batteries explode from my childhood. Not really as an adult, but as a child. Batteries are exploding all the time in my family. Recharging them. We had one blow out at a gas station when Mom started the car. I remember hearing a bang, and we looked under, and it was liquid dripping out. And the guy lifted the hood, and our battery had exploded right there at the gas station. Strange. And then I had one blow up in the garage with the charger, and then I had one blow up in the vehicle with the charger. My dad and my mom were going out for a dinner date or something. Anyway, I remember she was dressed up nice, and they go out to start the car, and then she comes running in the house in her dress, runs into the bathroom and gets in the shower with her clothes on. We're like, what the heck? Well, Dad had the battery on the charger, and he said, I'm going to start it, see if it'll start. So he gets in and he starts the car, and she said she saw the battery start to glow red. And she turned her head like that, and it blew up. Now, that's her story. I don't know. She maybe saw a flash of orange light from the hydrogen catching fire. But anyway, she saw some red, and she turned her head, and it blew up, and battery acid got on her clothes. And she had little pinprick holes in her polyester dress. It's in the 70s. So anyway, that's a traumatic experience as a kid, seeing your mom running through the house and getting in the shower with her clothes on. And yeah, there's more interesting stuff. These are fuel cells. We'll talk more about fuel cells in the future. So I know this is interesting, but we'll come back to it when we get to energy in the last part of the course.